Hello, I wanted to provide this quick update regarding a few questions that have arisen in working through assignment 3 for CE 849. And so the primary thing I want to talk about right now is a phenomenon that's referred to as endogeneity, and that is a potentially severe issue when we're trying to estimate regression models. Okay. And so endogeneity basically refers broadly to the circumstance where at least one of our explanatory variables of interest, so our predictor or covariate or independent variable, basically our x's, is correlated with the error term. And when that arises, we potentially could run into biased parameter estimates. So we could overestimate or underestimate the actual relationship between y and that specific x. And so in practice, when we estimate linear regression models using ordinary least squares, we presume that the predictor variables are exogenous or they're not correlated with the error term. And there are a number of situations where this assumption is violated, with three of the most widely known situations being the case where we have important omitted variables, where there is measurement error with respect to one of the predictor variables that we're including in the model, or where we have what's referred to as simultaneity, where we have the x and y essentially being determined concurrently based on the other variables that are included in that model. Okay. And so we'll provide brief coverage to each of these and then talk a little bit about the specific issues we run into with the data set for assignment 3. Okay. And so the first case, omitted variable bias. So oftentimes it may arise that we collect data with the intent of developing a model. We may have a model that appears reasonable to us, but there may be important information that explains the variability in y that we can't capture because that variable is simply not available for us. So either there's not a data source from which we can collect information about that variable, even though we may know it's important, or there may be a variable that's important or just simply ignorant to that fact. And so consequently, the model we're trying to estimate would generally take the following form you see here. And so we'll just keep these in terms of simple linear regression models, but the same phenomenon will hold when we run into the multiple regression case as well. And so in this circumstance, if there's an important variable that we're not actually observing, if in fact we could observe it, the correct or real form of that model would be as you see right here. So for example, there's some variable z, which is important, but we simply don't have knowledge about, okay? And so if we look at the functional forms of these two equations, it should hopefully become obvious that in this circumstance, this latter term, so the beta 2 times zi, the effects of that variable are essentially just going to be incorporated into this random error term epsilon, okay? And as a consequence of that, we're going to find that x and zi, unless they're completely independent of one another, so if these variables are completely unrelated, then this issue largely becomes a non-issue. However, if there's any degree of correlation, and if there's strong correlation particularly, we're basically going to find as a consequence that our parameter estimates are going to be biased as a consequence of that. And so consequently, there are a number of ways we can attempt to try to work around this, but in practice, it's very difficult for us to be able to detect that there's an omitted variable bias introduced, because simply we may not even be aware that that factor is important. And so this is just something to bring up. And as you think about estimating your models, as you pull variables in, you may find that some of your coefficients change in terms of their magnitude or even their sign. And so we talked a little bit about how that could be a concern as to multicollinearity, but it may just be the fact that that variable that is now included is important, and the variable whose sign has changed or whose magnitude has changed is less important when we account for these other omitted variables, okay? So this is a subtlety that's somewhat difficult for us to diagnose, and so we won't focus too much on it, but I just wanted to raise at least some degree of awareness of this issue. A second concern relates to measurement error, and so we talked about this example in the case of the noise measurement example. And so we can have measurement error in several different contexts. It could be with respect to our y variables or our x variables. Interestingly, if the measurement error is with our y variable or our dependent variable, there's not any particular concern. We'll still get consistent estimates of our parameter. The only issue that will arise there is that we'll basically have inefficient estimates, which means our standard errors will be larger than they should be because we're basically not measuring that y variable as accurately as we could in concept, okay? So in our case, if the noise meter was miscalibrated, we would end up with inefficient estimates, but they would at least be consistent. So it would be harder for us to reject the null hypothesis and find statistical significance in those results. Now, in contrast, if say the calipers we were using to measure the depth of the rumble strips were incorrect, then instead of measuring xi, where x is our rumble strip depth, we would actually be measuring some other variable, which we'll denote as xi star, okay? And so consequently, instead of estimating this model that you see right here, our xi would then instead take this alternate form here. And so consequently, as you can see from the way this model is worked out through the subsequent steps of combining common terms and so forth, you'll notice here that we've got correlation that's naturally arising here. And so our variable x, which again has been mismeasured, is going to depend on this error term, which we'll denote as vi, and then the fundamental error term, which we think we're estimating is epsilon, but is actually different here because it includes that term, is also dependent on v sub I. And so consequently, in this circumstance, we're going to run into the same situation where our slope estimates are going to be biased. And consequently, in this circumstance, we would end up, if we go back to the rumble strip example, to having an inaccurate assessment as to what the actual relationship is between rumble strip depth and noise levels, okay? A third case that arises, and this is one that's of particular concern to the homework assignment that we're currently working through, is we may have two variables that are co-determined with one another, okay? So basically, one variable affects the other and vice versa, or we may have essentially like a circular type relationship. So whenever we're estimating these regression models, we're basically operating under the assumption that X influences Y, but not that Y influences X. And so we may run into circumstances where one of those variables of interest affects Y, but in turn, Y also impacts that variable. And so pardon the steps in intermediate algebra that I'm skipping here, but what we'll find as a consequence of that is that instead of estimating these parameters beta 1 and beta 2 as an example, there are biases introduced, and the magnitude of those biases is a function of how strongly correlated those measures are with one another. But basically, what we'll tend to find in this scenario is if we try to use ordinary least squares, neither of these models will be correctly estimated. They'll both have concerns with endogeneity. And our inferences as to beta 1 and beta 2 and gamma 1 and gamma 2, for example, here, may all potentially be biased, okay? And so as we continue on in the example we worked through this week, we have some particular concerns that arise within the context of endogeneity. And so right now, I'm going to transition to SPSS and we'll walk through just a few of the fundamental questions that will arise as you work through this week's homework. Okay, and so as we see here, I've loaded our data set into SPSS. And as we look through this, you will also notice I've renamed these instead of arbitrary X1 to X14 labels. I've named them accordingly. I should also note our dependent variable of interest in this case is travel speed, which we need to actually calculate in our data set. And so you'd want to take the distance, which keep in mind is measured in tenths of a mile. So for this first observation, that traveler is going 4.4 miles, and they're doing so over 14 minutes. And so I don't particularly care what units you use, but I prefer to work in miles per hour. And so I would take that distance, divide that by 10, and then divide that collective quantity by the travel time in minutes, which I divide by 60 as an intermediate calculation so that the speed then comes in miles per hour, okay? And so the two variables that we are particularly interested in here as a consequence, interestingly, are whether distance and time have an impact on speed. And so at the onset here, we use both distance and time to calculate that speed metric. And so it would seem from the onset that we might have a problem here. Because if we think back to the simultaneity issue that was raised previously, presumably as one of those variables changes, the other variable is going to change as well. And so we'll quickly diagnose some of the issues that arise within this context by estimating a series of simple linear regression models, okay? And so what I'm going to do first of all is I'm going to estimate a model for travel speed as a function of distance, okay? And as a part of that, I'm going to save my predicted values and my residuals. And so we won't concern ourselves with these intermediate plots for the time being, but I just want to essentially demonstrate here what happens with those residuals. And so just looking at the model output here, we'll notice in this case, a simple linear regression, distance does appear to play an important role here. And so as our distance that the driver is traveling increases, so does their travel speed. Now we want to think a little bit about what that means from a practical standpoint. So why would that be the case, and does that make sense? But I don't want to do the whole homework assignment for you, and so we'll set that aside for the time being. But what this basically establishes for us is that there are some concern, is that there is apparently a relationship here between speed and the distance that that person has traveled, okay? And so from there, we are going to very quickly develop a few plots. And so first of all, we will plot our residuals versus our predicted values. And so in doing so, we'll see the output right here. And so no particular concerns here. We don't see any trends in the data, no increases or decreases. Variance is roughly constant. So essentially no concerns there. We will go back in and we'll develop a second plot. This time we'll look at our residuals versus distance. And so in doing so, you'll notice this also looks fairly good. I don't see any particular issues here. And so in the case of the simple linear regression, we really don't have any particular concerns, okay? And so what I'm going to do next is rerun this analysis. And so I'm going to estimate this model now for speed as a function of time. And so in doing that, we'll see again a strong linear relationship here. And so what we're finding, generally speaking, is that as our travel time decreases, or as our travel time decreases, our speed increases, or vice versa. As our travel time increases, our speed decreases. And so another item you might want to think about a little bit there in terms of what that means from a practical standpoint and how that result would arise given the nature of our data, okay? But back to our primary concerns here about our residuals. Keep in mind, I've estimated this a second time, so I've got a second set of residuals and predictions. So you want to be careful not to include the wrong or old set of residuals here as an example. But we look at this plot, and again, not any particular concerns here. So we've got a few points that are relatively large in terms of the magnitude of those residuals, but no real drastic concerns here when we look at residuals versus predictions. And subsequently, if we look at those residuals versus our X variable, which again, in this case is going to be our travel time, we'll basically see that same general relationship here. And so not any particular concerns here from just a cursory review of the data, okay? And so where do we go from here? Well, we're going to actually continue building this model, and now I'm going to include both distance and travel time in the speed prediction. And now in this case, what we're generally seeing here is that the direction of those effects is similar. So as distance increases, speed increases. As travel time increases, speed decreases. And now when we look at our residual plots, this time going to our third set of residuals and predicted values, we see that, oops, we have a problem here, okay? And so what we're tending to see here is at that very low values of predicted speed and at very high values of predicted speed, we're tending to significantly overpredict. And in the middle range there, we're tending to significantly underpredict. And so now just looking at this, and the question becomes, well, should we look at transforming our data, or what's driving this concern? And this is where it gets a little bit trickier even. And so what we're going to do now is we're going to look at these variables individually. So we'll look at our residuals versus travel time. And so in this case, you'll clearly see that when we plot the residuals versus travel time in this circumstance, we see that same trend developing. And so it seems like there's a problem with those variables, with that variable specifically. And we'll do the same thing now with distance rather than time. And so in this circumstance, we see that we're not running into that same problem here. And so consequently, it appears that our problem is with time as opposed to distance, okay? And so now we want to think, well, so why is that the case? So we had talked previously about how simultaneity is a problem, okay? So obviously, as our travel time changes from point A to point B, speed's going to change as a result of that as well, because you're using that travel time to calculate the speed. The question then becomes, though, well, why isn't distance a problem in this setting? And so if you think about that conceptually, just think about whether or not X influences Y and whether Y influences X. So in the case of travel time, clearly as our speed increases from point A to point B, distance being constant, the travel time is going to decrease as the speed increases. And likewise, as travel time increases, speed decreases and vice versa. And so those are used to calculate one another basically. And so as we think through this, the concern that arises here is if we think about the functional form of our model and the variables on the right-hand side affecting the variable on the left-hand side or vice versa. So there are compelling arguments we could make as to why if people are traveling a longer distance, their speed may be higher or lower as the case may be. In this case, our model suggests that speeds would be higher. In the case of travel times, it should be fairly obvious that as that travel time goes down, our speed is going to go up as a consequence. And so that's not necessarily telling us anything that's of particular interest from an inferential standpoint in terms of the effect of travel time, because likewise, as our speed increases, our travel time is going to go down. So we basically have a circular relationship here. And so as a consequence of that, what we'll find is that we have a clear example of endogeneity here. Now, why isn't that the case with distance as well? Because we're also using distance to calculate our speed. Well, as it turns out, if we increase our speed, is that changing the distance that we've traveled? Clearly not, right? And likewise, as we decrease our speed, there's no impact there on distance. And so there's not any sort of recursive circular relationship in that case, whereas in the instance of travel time, there very clearly is, okay? And so just an important thing to think through as we begin building our model. And so as a consequence of that, the net effect is that it's okay for us to include distance, but it's definitely not okay for us to include time for predictive purposes, okay? With that being said, you will probably want to think a little bit about the distance variable and why we might be seeing the trend that we're seeing in this case, because there are arguments that could be made for a positive or a negative sign or various magnitudes there if you think about what that distance variable may be capturing. But in any case, that's not what I want to emphasize here today. The one other point that's come up to this point is when we estimate these models, well, what constitutes a good model? How do we determine what we actually want to include here? And so I'm not going to give you too many tips here, but we'll include several of these predictor variables and we'll estimate a model here quickly. And we'll look at the results. And I guess it just so happens in this case that I was lucky and selected a relatively decent set of variables here. And so we've got distance traveled, gender, marital status, and number of children as our predictor variables. Several of these are statistically significant or relatively close to being statistically significant. So now the question becomes, well, which of these do I retain in my model? And so from that perspective, there's really two factors you want to consider as to the individual variables themselves. And so the first of those, is this variable statistically significant? If it is at alpha, say 0.05, then I would certainly suggest we include that in the model, okay? Now, whether that variable shows us an important relationship, and we used the example last time, so if it affects speeds by, say, a half mile per hour, is that giving us any useful insights? Now, even if it's not, I guess it would potentially still be of interest to include it. But then there's also the situation, what if a variable is of practical significance, seemingly, but it's not statistically significant? So let's say, for example, if we were just operating under the assumption that for whatever reason, we think there's significant differences in travel speeds between males and females. And so in this case, you'll notice that gender variable has a p-value of just under 0.2. And so it doesn't meet our significance level threshold, but maybe that is a meaningful result that we see a difference in speeds of roughly 1.6, 1.7 miles per hour, okay? And so in that circumstance, then we really need to make a choice. And so when I went through a statistics and econometrics course nearly 20 years ago, I guess at this point, but I was basically taught to retain variables if the t-statistic was at least 1, okay? And that's as arbitrary as the 0.05 threshold we talked about earlier for significance level. And so in that circumstance, why would we include those variables? And you can make an argument continuing along those lines that you would include every variable regardless as to whether or not it's statistically significant. Now, in part, we only have 151 observations here, and so we'll have natural limitations. We can't include 151 variables, for example, or we can't include, anything that's even a magnitude of that. And so as you're building your model, I would suggest that same rule that I learned. If the variable has a t-statistic of, say, at least 1, it might warrant inclusion, in part because we have a relatively small sample size here, 151 observations. And so if we had a larger sample, say 500 or 1,000, many of those variables may end up showing a significant relationship because those standard errors would be reduced as a consequence. Or if there's a variable that you thought going in would potentially show an interesting effect here, but simply doesn't. That information is perhaps as useful as finding a variable that is statistically significant, okay? And so I apologize for giving such loose and ambiguous guidance here, but it's really looking at a combination of those. So we are, of course, also interested in our R-squared and our adjusted R-squared, but interestingly, what we'll find there is there's not necessarily a direct correlation. So we can see improvements in our adjusted R-squared, even if some of these variables aren't statistically significant. And part of that relates to the degree to which these predictor variables are related to one another and some of the nuances as to these underlying relationships. But I guess the short answer here is, as you're building your model, you want to carefully balance statistical significance, practical significance, and then an important related element there is just whether or not those results make sense. And this relates back somewhat to the omitted variable issue we talked about previously. You may see some results that might seem weird or counterintuitive. And so in those instances, you could really go either way. You could argue to include it in the model and provide potential explanations as to why you're observing that phenomenon, or you could exclude it from the model. Now, if you do that, I would recommend when you write up your results that you do note that a relationship was found here, because we're not trying to certainly hide any facts as to the nature of our analysis there. but particularly if that variable introduces any other complications with respect to our model. And so unfortunately, regression building, it's not explicit. There's not a perfect formula in order to arrive at the best model. It's really looking at various aspects of our analysis and trying to develop a model that is as simple as possible, has as great of an explanatory or predictive power as possible, and contributes important knowledge that advances our understanding of, in this case, travel time, but whatever the topic may be that we're investigating, okay? And so if any of you have additional questions, please let me know. I'd be happy to record a few additional videos going into the weekend there, but thank you very much. I hope this helps.